All right, so we're talking about radioactivity, and radioactivity follows an exponential decay law. And we've seen that before with electricity when we had an RC circuit and other things, this decay. And so here's the equation. So this is the number of radioactive nuclei at some time t. N0 is the number that we start with. So here's time. Here's the number of nuclei remaining, right? So N0 is what we start off with. Then we have e to the minus RT. So R is called the decay constant. And don't forget, so here, n as a function of t equals N0 e to the minus RT. Now this can't have any units. And so we know that time is seconds, so R has to be 1 over seconds. So seconds to the minus 1 power. All right, so that's one equation, but it's not super useful. What people use more often than this is this. So another way of writing, instead of saying N0 e to the minus RT, some people say N0 e to the minus t over tau. So tau is called a time constant. And you know, tau is just 1 over r, right? So, or r is 1 over tau. Now, why would they want to do that? Well, it's actually real convenient because let's say that the time equals 1 tau. Well, if the time equals 1 tau, then this thing is just e to the minus 1. And most people that work with this kind of stuff know that e to the minus 1 is 0.37. So I mean, if you use this, you have to put in some horrible numbers. They might be this long or something like that. But here, again, if the time equals 1 tau, this is just e to the minus 1, bingo, 0.37. If the time equals 2 tau, you just put in that, right? So it would be e to the minus 2, which is this 0.13. So it's just easier, it's just easier to calculate it. All right. Now, actually, it's even more useful to use something called half-life. So this is the equation that we're going to use most of the time. So again, the number remaining at some particular time equals the number you start off with times 1/2 t divided by the half-life. And let me explain this half-life. So let's say this square, or whatever it is, represents the total number of radioactive nuclei initially. So after 1/2 will be gone. They'll decay. So that's after 1 half-life. After a second half-life, half of that will have decayed. After a third half-life, half of that will have decayed. So, I mean, it's just a nice conceptually easy way to think about it. So here you can see when the time is 1 half-life, half have decayed. So half are remaining. So if you would go into a nuclear medicine department at a hospital, and if you would ask somebody, if they know the decay constant or the time constant or the half-life, most, if not all, would say half-life, because that's what people in the real world work with. They work with half-lives. Now, what's interesting about the half-life is every isotope has a unique half-life. Before I show you that chart, here's just another helpful graph. So let's say we start off with 16 nuclei, all right? So we have 16 of these red nuclei. Now this is ridiculous, right? Because usually we have, a huge, gigantic number of nuclei. But this is just, it's a nice way to picture it. All right, so we have 16 reds at time equals 0. So after 1 half-life, half will decay. So we have half remaining. So here we go. 1 half-life, half. And so instead of having 16 reds, we have 8 reds. Now the reds have turned into greens, so we have 8 reds and 8 greens. So N0 divided by 2. After a second half-life, well, what's a half of a half? It's a fourth. So now we have N0 divided by 4. 1/4 N0. So half of these reds have turned into greens. So now we have 4 reds and 12 greens. After a third half-life, okay, half times a half is a fourth, times a half is an eighth. So we have N0 divided by 8. N0 divided by 8. And now we just have 2 reds and 14 greens. So that's kind of a nice way to think about it. And you can see this nice exponential decay. So here's a real, this is data. This is for carbon-14, which is radioactive. So the half-life for carbon-14 is about 6,000 years. So you can see that after 6,000 years, this is the fraction remaining, half. After another 6,000 years, a fourth. After another 6,000 years, an eighth, and so forth and so on. So it's just super convenient to use half-lives. It just makes it very easy. And this is what I was saying earlier. Every isotope has a unique half-life. You can see there's a huge range of half-lives. So carbon-14, like I said, 6,000 years. Strontium-90, 30 years. I-131, 8 days. Look at polonium-214, 0.00016 seconds, not very long at all. Radon, 4 days. Okay, now we have these that last a long, long time. So uranium-235, 0.7 billion years. Uranium-238, 4.5 billion years. And plutonium-239, 24,000 years. So in the United States today, we have all these nuclear power plants scattered throughout the country. And every nuclear power plant stores its own radioactive waste. And most of the radioactive waste are things like this that have really, really long half-lives. So years ago, the government wanted to build, well, the government thought, this is not so great having all this radioactive waste stored everywhere throughout the country. Maybe it would be best to just have it stored at one place and just keep it super secure. So they wanted to build it in Nevada. And of course, the people in Nevada were super not happy at all. And think about it. The half-life is, let's say, 1 billion years. That's one half-life. So how can you convince people that you can keep something safe, for billions of years? I mean, good luck. So anyway, it wasn't built. Maybe it will be one of these days. Who knows? But anyway, just look at this again. Here we have billions of years. Here we have 0.001 seconds. So these half-lives, they're all over the place. All right, now, so again, this equation is true and it's wonderful, but in the real world, how do you measure radioactivity? You have a meter, you have a Geiger counter. And so let's say you have a little piece of radioactive material right here. It's decaying, just pretend that's 360 degrees, right? Every single direction. Well, you're not going to be able to detect every single decay product because you just have your little meter here. So you're only measuring a certain fraction, So this is fine and dandy, but in the real world, this is what's measured. So this is called the activity or the decay rate. So the R stands for the rate, right? So how many nuclei are decaying? dN dt, or delta N delta T, all right? So you do a bunch of math, and it comes up to be the initial rate times 1/2 to the T over half-life. So it's similar to this, right? Instead of having the number remaining, you just have the rate, how many are decaying, decays per second. So the units of this, decays per second, and that's called a becquerel, because Becquerel was one of the early scientists who did a lot of work on this field. Now this is the modern unit, becquerel. However, a lot of people still use curies. So 1 curie is 3.7 times 10 to the 10th becquerels. So if you go, like I say, if you go into a nuke med department in a hospital and you talk to somebody who's kind of old, they're not going to know becquerels, they're going to know curies, because that's really what people have used for a long, long time. So let's do an example. Okay, and this is a true life example. So technetium, or Tech-99m, That's a typical isotope used for diagnostic nuke med. So Tech-99M has a half-life of 6 hours. A common dose for a diagnostic nuclear medicine scan is 20 millicuries. How much of this dose, and let's do it in millicuries and becquerels, remains after 24 hours? Now, there's a hard way to do this and an easy way to do this. And I like doing things the easy way. So I'm going to show you the easy way. What is so great? So the half-life is 6 hours, and we want to know how much is going to remain after 24. Well, look at those numbers. It's awesome. They are awesome. So 24 hours is 4 times the half-life, right? Half-life is 6 hours. So 24 hours is 4 half-lives. 4 half-lives. So how much is going to be left after the 24 hours? Well, we start off with the 20 millicuries. We start off with that, and then 4 half-lives. So 1/2 to the 4th power, right? 1/2. So this is what we start off with, 20 millicuries, and it's 1/2, and this is 4. So 4. So what's 1/2 to the 4th? 2 times 2 is 4, times 2 is 8, times 2 is 16. So it's 20 millicuries times 1 over 16. And that is 1.25 millicuries. So think about it. You know, you want to, you start off with 20 millicuries, but a day later it's only 1.25. So that's why, I mean, in the nuclear medicine department, first of all, the doctors, well, the people who prescribe the scans, it's usually early in the morning, because the nuclear pharmacists, they work in night and they get everything ready, you know, for the first thing in the morning, because you don't want it to decay away. So, I mean, if you're late to a nuclear medicine scan, everybody's going to be mad at you, basically, because the drug is not going to be, it's not going to have a high enough activity to do a good scan. Okay, now let's figure it out in becquerels. So we have 1.25 millicuries, and then the conversion factor is 3.7 times 10 to the 10th, 3.7 to the 10th, becquerels per, now you've got to be careful, what's a milli? It's times 10 to the negative 3 times 10 minus 3 curies. So we had to convert the millicuries, right, to curies. So you do that, and I promise you get 4.63 times 10 to the 7th becquerel. There you go. All right, so that's, so I mean, you always want to look for these numbers, you know. You want to see if this is a nice multiple of that. Makes it really, really easy. All right, now let's look at polonium. Polonium-210. The half-life is 138.38 days. So you think, wow, 138 days, it should all be gone, right? I mean, golly, the Earth's been around much longer than that, so why do we have any polonium? It should be all gone. Well, here's why we still have it. Because it's part of a decay chain. So you have U-238, 4.5 billion year half-life. So, you know, that decays into thorium. That's the half-life. That decays into protactinium, on and on and on and on and on. And then we make polonium-210. All right? So it's constantly being made because all these other isotopes are decaying. So that's a decay chain. All right, now we want to talk about the shell model of the nucleus. Remember, at the very first section of this chapter, we said, we got to explain that, we got to explain that, we got to explain that. Well, now we're going to explain a lot of the things that we discussed earlier. So the nuclear shell model. And again, it's just a model. So, I mean, it doesn't cover every single little tiny detail. It just covers most of the details. It's like in Physics 105, you know, when we talked about throwing objects, we didn't care if things were non-uniform, or like, think of a baseball. You know, baseball has the seams and the little threads and all that, and air resistance. We didn't worry about all that, right? We just made a simple model. Uniform sphere, no air resistance. Well, that's what this is. Nuclear shell model is just a model. All right, so here it is. So what we're going to assume is that every nucleon, every proton and neutron moves independently with some average potential energy. And the average potential energy is due to what? What are the forces? The attractive nuclear force, right? Okay, so there you go. Okay, now we always say that the potential energy is negative for attractive forces. Okay, so this is the potential energy diagram for the neutron, right? Because the neutron attracts other neutrons, the neutron attracts other protons. So it's all negative, you know? So here we have this finite potential energy well. We've talked about potential energy wells a long time ago. So the average neutron potential energy is due to the strong, you know, the nuclear strong force. All right, there you go. And again, notice it's millions of electron volts, not like chemistry. Now, what's different about the neutrons and the protons? Protons repel other protons. They attract other neutrons, but there's some repulsive, right? Now, the attractive force is a nuclear strong force, incredibly strong. The repulsive force is just electricity, which is not so strong, right? So, and remember, from back in the olden days, the potential energy for electricity, it was like, it went like this, right? It was proportional to 1 over the distance. And what does that look like? It looks like that, right? 1 over the distance looks like this. Okay, so what I'm saying, you have this part due to the nuclear strong force, which is negative because it's attractive, but then you have to lift it because of this positive part. And this is the 1 over r. So the average proton potential energy is due to the strong force and the electric force. Okay? And notice it doesn't go as deep as this one because we had this positive repulsive potential energy. Okay, now here's something that we're not doing the atomic physics chapter, but we're going to use one of the results from the atomic physics chapter, which is kind of no fair, right? So there's something called the Pauli principle. Okay, the Pauli principle basically says it gives you the maximum number of electrons or protons or neutrons that can fit in a particular energy level. All right? I mean, I think that's good enough. It just restricts the number of particles that can be in a particular energy level. Okay? That's all you really need to know. But I'll give you an example, don't worry. Okay, so we're going to take 2 cases. We're going to take the case where we have a small number of protons. Remember, Z is the proton number. So this is nuclei with Z less than about 8. Okay, so a small number of protons. So we'll do that case first because it's the easiest. Now, why do we want to do that? Well, if we have a small number of protons, there's not a whole lot of repulsive force, right? Or maybe I should say potential energy associated with electric repulsive force. So we can kind of ignore it, you know? So what I'm saying is, for a small number of protons, this is pretty small compared to this, so we're just going to ignore it. And that's okay. So you notice then that the neutron energy level looks exactly like the proton energy level because we've ignored the repulsive forces because they're small, because there's not a lot of protons. Okay, so this is what we would learn in the atomic physics chapter. Don't worry about it. I mean, you don't have to have it memorized, but just realize that the Pauli principle says you can only have 2 nucleons in this energy level. You can only have 4 nucleons in this energy level, 2 in this, and so forth. So that's just the Pauli principle gives it to you. Okay, now, let's see. So we have the neutrons here, protons here. This is the potential energy in MeV. Okay, the neutron radial distance is measured to the left. I don't really care, right? There's a distance. These are the first three allowed energy levels. They're spaced MeV apart. These are the maximum number of nucleons allowed by the Pauli principle, right? 2, 4, 2. The proton potential energy is nearly identical to the neutron potential energy when Z is small. Okay, now, who cares? How do you use it? Here, this is how you're going to use it. So, this is carbon 12. Carbon 12. Now look, what do you notice about the energy levels? Well, 2 is the max, we have 2. 4 is the max, we have 4. Over for protons, 2 is the max, we have 2. 4 is the max, we have 4. So what does that say? It says that the energy levels are full. What does that mean? That means, just like in chemistry, you know, it means that the nucleus is incredibly stable. It's tightly bound. It has a high binding energy. All right? Well, gee, where did we see that before? How about that? So this is carbon 12. Oh, uh-oh, don't do that. So look at it. Carbon 12 has a high binding energy, right? It's super, super stable. You could work out similarly for helium-4 and oxygen-16, and you would see for all three of these, their energy level diagrams are all full. Okay, they're all full, so they have incredibly high energy, binding energies, and they're super, super stable. On the other hand, let's look at boron 12. Now this is the picture for carbon 12. Now boron has 5 protons, you know, not 6 like carbon 12, right? All right, so what I want you to do is please draw a similar graph for boron 12. All right, so draw a similar graph, but for boron. So pause your video and draw it. All right, I assume you've done that, so let's look at it. So boron, 5 protons, 1, 2, 3, 4, 5, and it's 12, so 7 neutrons, 1, 2, 3, 4, 5, 6, 7. Now look, maximum 2, 2, maximum 2, 2. Here's a maximum 4, but we only have 5 protons, right? So we're just going to put 3 there. Okay, here maximum 4, we have a 1, 2, 3, 4. But remember, there's 7, so 1, 2, 3, 4, 5, 6. So we got to put this one on the next one, right? Okay, now look at that. What do you notice? What's true about the neutrons? We have one extra one, right? We want to have a full energy level, but we get this goofball, right? It's not full. You know, we'd want 2 to be full here. So there's 1 too many, okay, to have a complete level. What do you notice about this? It's missing one, right? It wants to have all those levels full to be super stable, and it's missing one. So here there's 1 too many. Here there's missing one. So how could we make this situation better? In other words, how could we make this boron have a super, super strong, stable nucleus? What could we do? Well, it's pretty obvious, right? Just put that over there. Well, what does that mean? So what that means, we're converting a neutron into a proton, right? We're converting a neutron into a proton. Have we ever done that before? Yeah. What's that called? It's called beta decay, right? Or beta minus decay. So the neutron becomes a proton, plus electron, plus the antineutrino and energy. Okay? So that's how this thing can become more stable, by undergoing beta decay. So let's see, all right, so this is all talk, right? You know, we're saying, okay, if this thing beta decayed, it would become more stable. Well, let's see if it really happens. So you look at the chart. Here it is, boron 7. By golly, what does it do? Beta minus. Okay, so it's radioactive, and it undergoes beta minus emission to become more and more stable. Let's do another example. Let's do nitrogen 12. So once again, pause your video and draw the similar diagram for nitrogen 12. Okay, I assume you've done that. So let's see. So we have 7 protons, right? So there's going to be one extra one, right? 1, 2, 3, 4, 5, 6, 7. And 12 minus 7 is 5, so there's 5 neutrons. 1, 2, 3, 4, 5. So what do you notice? We have one extra, right? We want to have 2 up here, not 1, so that's an extra one. We want to have 4 here, we only have 3. So what would be a great way to what would this thing want to do to become more and more stable? We want this proton now to become a neutron. Well, does that happen? Yeah, it sure does, right? That's beta plus. The proton becomes a neutron plus the beta plus, the positron plus the neutrino. So, all right, so that's, theoretically you would think in order for this thing to become stable, this is what's going to happen, a beta plus emission. Well, let's see if it happens. Ta-da! Nitrogen 12, beta plus. Okay, so that's great. So this shell model, does a great job in predicting the decay mode for these isotopes where Z is small. All right. Now, let's, hold on a second. Now, hold on just a minute. Look at this, though. Well, let me go back. Yeah, look at this. Now, remember, forget it. That's okay. Here, this emits energy, right? Because the mass of the neutron is greater than the mass of the proton. So some of this mass becomes energy. But what do we have now? Right? So this has less mass than that. So this is only going to occur when this thing somehow gains energy. Okay? This has to have extra energy. Okay. Anyway. All right, so that's small z. What about large z? Okay, what about large z? So let's just look at what do we see? Now for large z, that means we have a lot of protons. So there's a lot of repulsive forces, right? So there's a lot of positive potential energy, So you can't ignore this 1 over r like we could before. So once again, since this is negative, this is positive, this whole thing gets pushed up. All right. Okay, so that's just what do we observe? Well, we observe that this thing, this is much more negative than that, which I just explained, right? So the neutron well is much deeper than the proton well. But look, we also notice that these heights are pretty much the same, right? They're pretty much the same. And also we notice there's many, many more neutron states than are proton states. Okay. Right? So neutrons and protons fill energy levels to the same height. Okay, so this is what we notice. Now why? Well, I already explained the business about we have the positive potential energy because of the protons repelling each other. That's why the whole thing is pushed up. Okay, now why are these heights pretty much the same? Well, if they weren't the same, what would happen? We just have beta minus beta plus decays until they become the same, Okay, so that makes more sense. Now look here. Here we have, again, we have way more neutron states than proton states. Where have we heard that before? Remember this? So this is the line of stability, right? The line of stability does not follow the n equals z line. It follows this curve. Right? And remember why? Because the neutrons undergo that strong nuclear force, so they're needed to hold the nucleus together, right? The more neutrons, the more nuclear strong force and the more stability. So yeah, so we're going to have more neutrons than protons, which is what it says. Yeah, wonderful. Okay, so anyway, so all I'm saying is that this shell model, it does a good job of explaining a lot of the data. All right, now let's talk about something called radioactive dating. Actually, let's quit.